Subscribe to the channel so you don't miss out on any of these videos. The universe is full of mysteries, but few are as fascinating as the story of what came before light could shine. Imagine a universe not bathed in starlight or cosmic glow, but one where photons, the very particles of light we take for granted, were trapped, bouncing endlessly in a dense, chaotic sea of particles. It was an era that shaped everything we see today, and yet, it's an era that remains hidden, locked away in the fabric of time. This is the story of the Photon Epoch, a time so crucial to the universe's history that without it, nothing we know could exist. But what really happened during this time? And how did it pave the way for the universe we live in? Let's break it down. To understand the Photon Epoch, we need to go back, way back. We're talking just a few 100,000 years after the Big Bang. A time so early in the universe's history that the very laws of physics were still cooling off and settling into what we now understand. In the moments immediately following the Big Bang, the universe was unimaginably hot and dense. Temperatures soared to billions of degrees, and matter existed in a state so extreme that the particles forming atoms, protons, neutrons, and electrons, couldn't even hold together. Instead, the universe was a chaotic plasma soup, a mix of charged particles and energy. Here's the thing about light. For photons to travel freely, they need space. But during the Photon Epoch, there wasn't any space for them to move. The dense plasma was so thick and impenetrable that photons couldn't escape. They were constantly colliding with electrons, unable to break free or travel more than a fraction of a millimeter. This made the universe opaque. Imagine being in the densest fog you could think of, only this wasn't fog. It was a blinding, impenetrable sea of energy. Now, this might sound like chaos, but it was also a period of incredible transformation. The energy from these trapped photons was vital, constantly interacting with matter, shaping the early structures of the cosmos. The entire universe was expanding and cooling, but it wasn't doing so evenly. Tiny fluctuations in density were forming, the seeds of what would eventually grow into galaxies, stars, and planets. As the universe expanded, it cooled. And as it cooled, the conditions began to change. Around 380,000 years after the Big Bang, something extraordinary happened. The universe reached a temperature where protons and electrons could combine to form neutral hydrogen atoms. This process is called recombination, but don't let the name fool you. It wasn't like these atoms had been together before. It was the first time they could exist as stable, neutral particles. This was the turning point. Neutral hydrogen doesn't interact with photons in the same way plasma does. So, when recombination occurred, the universe suddenly became transparent. The photons that had been trapped for hundreds of thousands of years were now free to travel across space. This moment gave birth to the cosmic microwave background CMB, the faint glow of radiation that still exists today and serves as a snapshot of the universe at that time. The cosmic microwave background is like a baby picture of the universe. It tells us what the cosmos looked like at the moment photons were finally able to move freely. But it also carries the imprint of everything that happened during the Photon Epoch, the density fluctuations, the interactions between particles, and the overall structure of the universe. Scientists have studied the CMB extensively, using it to unlock secrets about the universe's age, composition, and even its future. But let's not skip over the sheer complexity of the Photon Epoch itself. During this time, the universe was governed by processes that are difficult to wrap our heads around. For instance, photons weren't just bouncing aimlessly, they were part of a delicate balance. Their energy was intertwined with the matter around them, shaping the behavior of particles and influencing the large-scale structures of the cosmos. The way photons scattered off electrons, a process known as Thomson scattering, played a huge role in how energy was distributed across the universe. And then there's the mystery of how this era connects to what came next. As the universe transitioned from being opaque to transparent, it didn't do so all at once. It was a gradual process, with different regions becoming transparent at slightly different times. This uneven transition created subtle variations in the CMB, patterns that scientists have mapped out in incredible detail. These patterns aren't random. They're the fingerprints of the early universe, revealing clues about everything from the presence of dark matter to the nature of inflation, the rapid expansion that occurred right after the Big Bang. What's even more mind-blowing is that we wouldn't know any of this if it weren't for advances in technology. Instruments like the Planck satellite and the Wilkinson microwave anisotropy probe, WMAP, have allowed us to study the CMB with incredible precision. They've given us a window into the Photon Epoch, showing us not just what the universe looked like, but how it behaved in its earliest stages. Yet, for all we've learned, there's still so much we don't understand. The Photon Epoch is like a puzzle with missing pieces, a chapter of the universe's history that holds countless secrets. For instance, what role did dark matter play during this time? Dark matter doesn't interact with photons, so it was invisible during the Photon Epoch. But its gravitational influence was there, shaping the density fluctuations that would later grow into galaxies and clusters. Scientists are still trying to figure out exactly how dark matter influenced the Photon Epoch and how its effects can be traced in the patterns of the CMB. And then there's the question of what came before. The Photon Epoch marks the end of the universe's dark age. But what about the time before that? What conditions led to the creation of the plasma in the first place? Could there have been processes we don't yet understand, phenomena that shaped the universe in ways we can't even imagine? The Photon Epoch isn't just a period of history, it's a key to understanding the universe as a whole. By studying this era, we can piece together how the cosmos evolved from a hot, dense plasma to the vast, complex expanse we see today. It's a story that spans billions of years, connecting the smallest particles to the largest structures in existence. And it all began with photons, trapped in a universe that wouldn't let them shine. The story of the Photon Epoch doesn't just stop with the universe cooling and photons breaking free. In fact, the ripples it left behind continue to shape our understanding of the cosmos even now. To fully grasp how pivotal this epoch was, let's dive deeper into its aftermath and the chain reaction it set off across cosmic history. When the universe transitioned from being a dense plasma to a transparent expanse filled with freely traveling photons, it created an environment where gravity could take center stage. During the Photon Epoch, the immense pressure of radiation had counteracted gravity's ability to pull matter together. But once the photons were no longer interacting with the plasma, radiation pressure dropped, and gravity began its relentless work. This marked the beginning of a new era, the formation of the first large-scale cosmic structures. Those tiny fluctuations in density we mentioned earlier? They became the scaffolding for galaxies, stars, and all the celestial wonders we see today. Areas that were slightly denser during the Photon Epoch started to pull in more matter, growing into the vast clusters of galaxies we observe in the universe now. Without the patterns imprinted during this epoch, the cosmos would lack the structure and diversity that make it so awe-inspiring. But let's rewind a bit. Why were these density fluctuations there in the first place? The answer lies in an even earlier era, the period of cosmic inflation. Inflation was a mind-bogglingly rapid expansion of the universe that occurred mere fractions of a second after the Big Bang. During this time, quantum fluctuations, tiny, random variations at the smallest scales, were stretched to cosmic proportions. These fluctuations created the initial seeds of density variations, which were then amplified during the Photon Epoch and became the foundation of cosmic structure. Here's where it gets even more intriguing. The precise pattern of these fluctuations, as recorded in the cosmic microwave background, is like a fingerprint of the early universe. Scientists can use this pattern to test theories about the nature of the cosmos, from the properties of inflation to the behavior of dark matter and dark energy. The CMB isn't just a snapshot of the universe at one moment in time, it's a treasure trove of information about the forces that shaped everything. One of the most fascinating aspects of studying the Photon Epoch is how it reveals the interconnectedness of the universe. For instance, the physics of this era is closely tied to the concept of baryon acoustic oscillations, BAOs. These are sound waves that rippled through the plasma before the universe became transparent. The interaction between photons and matter during the Photon Epoch created pressure waves that left behind subtle imprints in the distribution of galaxies. Even today, we can see evidence of these oscillations in the large-scale structure of the universe. Understanding the Photon Epoch also gives us a glimpse into one of the biggest mysteries of modern cosmology, the nature of dark energy. The CMB not only provides clues about the early universe but also helps scientists study its long-term evolution. By examining how the universe has expanded over time, researchers can infer the influence of dark energy, the mysterious force driving the accelerated expansion of the cosmos. But despite all this progress, the Photon Epoch remains shrouded in mystery. One of the most puzzling questions is how the universe achieved such incredible uniformity. On large scales, the CMB shows that the universe was remarkably smooth, with only tiny variations in temperature and density. Yet, without cosmic inflation, there wouldn't have been enough time for distant regions of the universe to become so similar. Inflation explains this by suggesting that the entire observable universe was once contained within an infinitesimally small region, allowing it to become homogeneous before expanding to its current size. Even so, there are anomalies in the CMB that challenge our understanding. For example, scientists have observed slight asymmetries in the temperature distribution of the CMB, as well as unexplained cold spots. These anomalies could point to new physics or reveal hidden aspects of the universe that we have yet to uncover. Could they be relics of unknown processes during the Photon Epoch? Or are they hints of something even deeper, perhaps connected to the multiverse or higher dimensions? Another compelling area of research is the role of neutrinos during the Photon Epoch. Neutrinos are incredibly elusive particles that barely interact with matter, making them difficult to study. However, they played a significant role in the early universe, influencing its dynamics during the Photon Epoch. The way neutrinos decoupled from the plasma, similar to how photons later broke free, provides valuable insights into their properties and how they fit into the broader picture of particle physics and cosmology. Speaking of particles, let's not forget about the mysterious dark matter. While it doesn't emit or absorb light, and therefore doesn't show up in the CMB directly, its gravitational effects were crucial during the Photon Epoch. Dark matter provided the underlying framework for the density fluctuations we see in the CMB, acting as an invisible web that guided the formation of cosmic structures. Understanding how dark matter interacted, or didn't interact, with the plasma during this era is one of the biggest challenges in cosmology. What makes the Photon Epoch so captivating is that it's a story of contrasts. It was a time of incredible chaos and order, simplicity and complexity, transparency and opacity. It was the universe's first major transformation, a moment when light itself was set free to illuminate the cosmos. And yet, it's also a reminder of how much we still don't know. For every question the Photon Epoch answers, it raises new ones, pulling us deeper into the mysteries of the universe. Perhaps what's most remarkable about the Photon Epoch is its enduring legacy. The photons released during this time have traveled across the cosmos for billions of years, carrying with them the story of the universe's infancy. They've been stretched by the expansion of space, cooled to just a few degrees above absolute zero, and now form the faint glow of the cosmic microwave background. They are the universe's oldest messengers, a constant reminder of where we came from and how far we've come. The legacy of the Photon Epoch doesn't just rest in the photons themselves but also in the information they carry about the universe's origins and its ultimate fate. These photons, now stretched into microwaves, act as a cosmic time capsule, carrying with them an imprint of the conditions that existed nearly 13.8 billion years ago. By studying them, scientists can uncover astonishing details about how the universe came to be, how it evolved, and even speculate about its eventual destiny. One of the most profound discoveries tied to the Photon Epoch is the near-perfect isotropy of the cosmic microwave background, CMB. While the CMB is nearly uniform in all directions, the tiny variations that do exist tell a story of quantum fluctuations stretched across the vast expanse of the cosmos. These fluctuations, preserved as density and temperature variations, reveal the intricate dance between matter and radiation during the Photon Epoch. Let's take a closer look at these fluctuations. The variations in the CMB's temperature are measured in millionths of a degree, but they hold the key to understanding the universe's large-scale structure. Regions of slightly higher density correspond to slightly higher temperatures in the CMB, while lower density areas are cooler. These temperature differences weren't random. They were shaped by the interplay of gravity, radiation pressure, and the primordial soup of particles that existed at the time. During the Photon Epoch, baryonic matter, the normal matter that makes up stars, planets, and people, was tightly coupled with radiation. This coupling caused waves to propagate through the plasma, creating regions of compression and rarefaction. These acoustic oscillations left a distinctive pattern in the CMB, one that scientists have been able to measure with incredible precision thanks to missions like COBE, WMAP, and Planck. The Planck satellite, in particular, has provided some of the most detailed maps of the CMB to date. These maps allow researchers to analyze the size and distribution of the fluctuations, revealing critical information about the universe's composition, its rate of expansion, and even the curvature of space itself. For example, the CMB tells us that the universe is flat, meaning that its geometry is neither curved like a sphere nor saddle-shaped. This flatness is a direct consequence of the conditions set during the Photon Epoch. Another remarkable insight gleaned from the CMB is the precise breakdown of the universe's components. By analyzing the spectrum of the CMB, scientists have determined that the universe is composed of about 5% ordinary matter, 27% dark matter, and 68% dark energy. This composition was effectively locked in during the Photon Epoch, making this era a crucial turning point in cosmic history. The Photon Epoch also sheds light on the mysterious concept of recombination. While the term might sound like something out of a sci-fi movie, it refers to the process by which free electrons combined with protons to form neutral hydrogen atoms. This event, which marked the end of the Photon Epoch, was critical because it allowed photons to travel freely, creating the CMB. Before recombination, the universe was like a foggy soup of particles. Photons were constantly scattering off free electrons, unable to travel far before being deflected. But as the universe cooled, the energy levels dropped enough for electrons to bind to protons, forming neutral hydrogen. With fewer free electrons to scatter them, photons could finally escape, flooding the universe with the first light we can still detect today. But recombination wasn't instantaneous. It was a gradual process, taking place over tens of thousands of years. During this time, small pockets of the universe became transparent at slightly different rates, leaving subtle imprints in the CMB. These variations provide clues about the universe's temperature, density, and even its expansion rate at the time. While the Photon Epoch provides a detailed snapshot of the universe at a specific moment in time, it also serves as a bridge to understanding its broader evolution. For instance, the density fluctuations preserved in the CMB set the stage for the formation of the first stars and galaxies. Over time, these small variations grew under the influence of gravity, eventually forming the complex web of cosmic structures we see today. The Photon Epoch also offers a unique window into the physics of the early universe. By studying the interactions between photons, baryons, and dark matter during this period, scientists can test theories about fundamental forces and particles. For example, the way photons interacted with matter during the Photon Epoch depends on the exact properties of the particles involved, such as their masses and charges. Any deviations from the predicted behavior could reveal new physics beyond the standard model. One of the most tantalizing possibilities is that the CMB could contain evidence of new particles or forces. For example, some theories suggest that dark matter might interact weakly with photons or baryons during the Photon Epoch, leaving subtle imprints in the CMB. Similarly, the properties of neutrinos, ghostly particles that barely interact with matter, can be inferred from their influence on the CMB's fluctuations. Even more intriguingly, the Photon Epoch might hold clues about the nature of dark energy. While dark energy didn't dominate the universe during this era, its effects can still be seen in the CMB's patterns. By studying these effects, scientists hope to unravel the mystery of why the universe's expansion is accelerating and what this means for its ultimate fate. The Photon Epoch also connects to the concept of cosmic inflation, the brief but dramatic expansion of the universe that occurred before the epoch began. Inflation not only set the stage for the density fluctuations seen in the CMB, but also left behind its own unique imprints. For example, inflation predicts a specific pattern of polarization in the CMB, which scientists are actively searching for. Detecting this pattern would provide direct evidence of inflation and open a new window into the earliest moments of the universe. Despite all the progress we've made in understanding the Photon Epoch, many questions remain unanswered. For instance, while we've mapped the CMB in incredible detail, we still don't fully understand the anomalies it contains, such as the cold spot, or the slight asymmetries in its temperature distribution. These features could be statistical flukes, or they might point to new physics beyond our current understanding. As our technology improves, so too does our ability to probe the Photon Epoch in even greater detail. Future missions, such as the proposed CMB-S4 experiment, aim to measure the CMB with unprecedented precision, potentially revealing new insights into this critical period of cosmic history. These missions could help answer some of the most profound questions in cosmology, from the nature of dark matter and dark energy to the origins of the universe itself. The Photon Epoch is more than just a chapter in the universe's history, it's a foundation for understanding everything that came after. It's a reminder of the incredible complexity and interconnectedness of the cosmos, a testament to the power of light to illuminate even the darkest corners of our understanding. And as we continue to explore its mysteries, we can't help but marvel at the sheer beauty of the universe's story, written in the faint glow of the cosmic microwave background. The Photon Epoch remains one of the most captivating and significant eras in cosmology, not just for what it reveals about the past, but for the doors it opens to understanding the universe's future. The faint glow of the cosmic microwave background CMB, the epoch's most enduring legacy, carries with it a wealth of information that researchers are only beginning to fully decode. One of the intriguing aspects of the Photon Epoch is how it relates to the idea of a cosmic fingerprint. The temperature fluctuations and polarization patterns in the CMB aren't just random, they are the fingerprints of processes that occurred during and immediately after the Photon Epoch. These fingerprints act like a crime scene, offering scientists clues to reconstruct the events that shaped the universe in its infancy. Among the most significant discoveries tied to these fingerprints is the power spectrum of the CMB. This spectrum, which plots the intensity of temperature fluctuations at different scales, contains a series of peaks and troughs. These peaks correspond to the acoustic oscillations of the photon-baryon plasma during the Photon Epoch. By analyzing their exact positions and heights, scientists can derive critical information about the universe's properties, such as its total energy density, the proportion of dark matter, and even the speed of sound in the early universe. The concept of sound waves in the early universe might seem strange at first. After all, we tend to think of space as silent and empty. But during the Photon Epoch, the universe was filled with a hot, dense plasma that allowed sound waves, technically pressure waves, to travel through it. These waves were driven by the competing forces of gravity and radiation pressure. Regions of higher density collapsed under their own gravity, creating compression zones, while radiation pressure pushed outward, creating rarefaction zones. The interplay of these forces created oscillating waves that left an indelible mark on the CMB. What makes these acoustic oscillations so fascinating is their scale. The largest oscillations, corresponding to the first peak in the power spectrum, represent regions where gravity and radiation pressure were perfectly balanced at the moment of recombination. Smaller scale oscillations, corresponding to subsequent peaks, reflect higher harmonics of this fundamental wave. The relative strengths of these peaks reveal a treasure trove of information about the universe's composition and dynamics during the Photon Epoch. For example, the relative heights of the first and second peaks in the power spectrum provide a direct measure of the density of baryonic matter. Meanwhile, the third peak's height is influenced by the density of dark matter. Together, these peaks allow scientists to weigh the universe and determine the proportions of its various components with remarkable accuracy. This detailed picture of the universe's composition is one of the greatest achievements of modern cosmology, and it owes much to the Photon Epoch. The Photon Epoch also serves as a natural laboratory for studying the fundamental forces of nature. During this period, the universe was governed by the same physical laws that operate today, but the extreme conditions of high temperature and density brought these laws into sharp focus. By analyzing the behavior of photons, baryons, and dark matter during the Photon Epoch, scientists can test theories about the fundamental interactions between particles. One area of active research involves the possible interactions between dark matter and ordinary matter or photons. Most current models assume that dark matter interacts only gravitationally, but some theories propose additional interactions that could have subtle effects on the CMB. For instance, if dark matter particles had a small but non-zero coupling to photons during the photon epoch, this could alter the pattern of fluctuations in the CMB. Detecting such effects would revolutionize our understanding of dark matter and its role in the cosmos. Another tantalizing possibility is that the photon epoch might hold clues about the nature of neutrinos. These elusive particles, which interact only weakly with matter, played a significant role during this period. Neutrinos decoupled from the rest of the universe's matter and radiation slightly earlier than photons, creating a neutrino background that predates the CMB. While we can't directly observe this background, its effects can be inferred from the CMB's power spectrum. By studying these effects, scientists can learn about the properties of neutrinos, such as their masses and the number of distinct types, or flavors, that exist. The photon epoch also offers insights into the initial conditions set by cosmic inflation. Inflation predicts that the density fluctuations observed in the CMB should follow a nearly scale invariant pattern, meaning that fluctuations of different sizes should have roughly the same amplitude. This prediction has been confirmed to an astonishing degree of precision by observations of the CMB, providing strong evidence for the inflationary model. However, there are still open questions about the exact mechanism of inflation and the nature of the inflaton field that drove it. By probing the imprints of inflation in the CMB, scientists hope to answer these questions and gain a deeper understanding of the universe's earliest moments. One particularly exciting avenue of research involves the search for primordial gravitational waves. These ripples in spacetime, predicted by some inflationary models, would have left a distinctive pattern in the polarization of the CMB. Detecting this pattern would not only provide direct evidence for inflation but also offer a glimpse into the energy scales at which it occurred, energies far beyond what can be achieved in any laboratory on Earth. As researchers delve deeper into the photon epoch and its legacy, they are also confronting some intriguing anomalies in the CMB. For instance, the so-called cold spot is a region of the CMB that appears significantly cooler than expected. While it could be a statistical fluke, some theories suggest it might be evidence of new physics, such as the influence of a cosmic supervoid or even a collision with another universe. Similarly, the slight asymmetry in the CMB's temperature distribution between different hemispheres challenges the assumption of perfect isotropy and could hint at unknown processes during the photon epoch. The photon epoch is not just a relic of the distant past, it is a cornerstone of our understanding of the universe as a whole. The light that was released at the end of this epoch continues to shape our view of the cosmos, providing a snapshot of a universe that was both simpler and more chaotic than the one we see today. As we continue to explore its mysteries, we are reminded of the profound interconnectedness of all things, from the tiniest quantum fluctuations to the largest structures in the cosmos. This era, where photons were trapped in a cosmic dance with matter, serves as a testament to the power of light to reveal the secrets of the universe. It is a story of transformation, of emergence from chaos into order, and of the enduring quest to understand our place in the vast expanse of space and time. The photon epoch is a story not just of what happened, but why it matters to our understanding of everything around us. To grasp its profound importance, it's essential to recognize that this era didn't just set the stage for the universe as we know it, it encoded a vast amount of information that continues to shape modern cosmology. Every observation we make of the cosmic microwave background CMB is like peeling back layers of a cosmic onion, each one revealing a new facet of this epoch's impact. One of the most compelling mysteries tied to the photon epoch is its role in seeding the large-scale structure of the universe. The acoustic oscillations of the photon baryon plasma, which left their imprint on the CMB, also influenced the distribution of matter in the universe. These oscillations created density fluctuations that served as the scaffolding for galaxy formation. Regions of higher density in the plasma attracted more matter due to gravity, eventually collapsing to form the galaxies, clusters, and filaments we see today. This connection between the CMB and large-scale structure is a remarkable example of how the universe's earliest moments resonate across billions of years. One particularly fascinating phenomenon linked to this process is known as baryon acoustic oscillations, BAO. These are the remnants of the sound waves that traveled through the photon-baryon plasma during the Photon Epoch. When the universe cooled and photons decoupled from matter, these waves effectively froze in place, leaving a characteristic scale imprinted on the distribution of galaxies. By measuring the BAO scale in the distribution of galaxies, astronomers can determine the universe's expansion history and refine their estimates of key cosmological parameters, such as the Hubble constant. The precision with which we can measure these parameters owes much to the detailed study of the CMB. For instance, the density of dark matter, an enigmatic component that makes up about 27% of the universe's total energy density, can be inferred from the relative heights of the peaks in the CMB power spectrum. Similarly, the density of dark energy, which drives the accelerated expansion of the universe, can be constrained by comparing the CMB's predictions with observations of the present-day universe. These connections highlight the Photon Epoch's pivotal role as a bridge between the universe's primordial state and its current structure. Another intriguing aspect of the Photon Epoch is its potential to reveal physics beyond the Standard Model. The Standard Model of particle physics describes the behavior of known particles and forces with extraordinary precision, but it leaves many questions unanswered. For example, it does not account for dark matter or explain why the universe contains more matter than antimatter. The Photon Epoch, with its extreme conditions and sensitivity to subtle effects, provides a unique testing ground for new theories. One area of active research involves the potential influence of exotic particles on the CMB. Some models of dark matter propose the existence of particles that interact weakly with photons or baryons, leaving subtle imprints on the CMB's temperature and polarization patterns. Similarly, theories involving additional neutrino species, beyond the three flavors currently known, could alter the expansion rate of the universe during the Photon Epoch, changing the timing of recombination and the resulting CMB fluctuations. Detecting such effects would be a groundbreaking achievement, offering direct evidence for new physics. The Photon Epoch also intersects with one of the biggest questions in cosmology: the nature of inflation. Inflation, the rapid exponential expansion of the universe that occurred a fraction of a second after the Big Bang, set the initial conditions for the Photon Epoch. It stretched tiny quantum fluctuations into macroscopic density variations that later became the seeds of cosmic structure. While inflation is widely accepted, its exact mechanism remains mysterious. Was it driven by a single scalar field, or did multiple fields play a role? What was the energy scale of inflation, and what does it tell us about the unification of forces in the early universe? The CMB offers a unique window into these questions. In addition to the temperature fluctuations that reveal the density variations seeded by inflation, the polarization of the CMB contains information about primordial gravitational waves. These waves, predicted by many inflationary models, would leave a distinctive B-mode pattern in the polarization. Detecting this pattern would provide direct evidence for inflation and help pinpoint its energy scale. While current observations have placed stringent limits on the strength of primordial gravitational waves, future experiments hold the promise of unlocking this critical piece of the puzzle. As we delve deeper into the mysteries of the Photon Epoch, we are also confronted with its limitations. The CMB represents the last scattering surface, beyond which photons could not travel freely. This makes it the farthest back in time we can see using electromagnetic radiation. However, the universe's story doesn't begin with the Photon Epoch. It stretches further back to the era of quantum fluctuations and the first moments of the Big Bang. To explore these earlier epochs, scientists are turning to other messengers, such as neutrinos and gravitational waves. Neutrinos, which decoupled from the rest of the universe's matter and radiation slightly earlier than photons, carry information about the universe's state during the neutrino decoupling epoch. Detecting the cosmic neutrino background, the relic neutrinos from this period, would open a new window into the universe's infancy. Similarly, gravitational waves, ripples in spacetime caused by violent events or quantum fluctuations during inflation, could provide a direct probe of the universe's earliest moments. While detecting these signals is an enormous technical challenge, ongoing advancements in observational techniques offer hope for breakthroughs in the coming decades. The Photon Epoch also serves as a reminder of the profound interconnectedness of all things. The photons that decoupled from matter during this era have traveled billions of years to reach us, carrying with them a record of the universe's past. They remind us that the light we see in the night sky, whether from stars, galaxies, or the CMB itself, is not just a snapshot of distant objects but a time capsule that connects us to the very origins of the cosmos. The story of the Photon Epoch is one of transformation, from a hot, dense, and opaque universe to one where light could finally shine. It is a story of discovery, as scientists unravel the secrets encoded in the CMB to reconstruct the universe's history. And it is a story of possibility, as we look beyond the Photon Epoch to explore the unknown frontiers of cosmology. As we continue to probe the mysteries of the Photon Epoch, we are reminded of the words of Carl Sagan. We are a way for the cosmos to know itself. By studying this epoch, we are not just learning about the universe's past, we are also uncovering the forces that shaped its present and will determine its future. In doing so, we are fulfilling a fundamental human drive to understand the cosmos and our place within it. The Photon Epoch represents a cosmic symphony, where the orchestra of particles and forces played a tune that would echo across the eons. Yet, the deeper we dive into this era, the more questions we encounter, each more profound than the last. What were the precise mechanisms that governed the interactions of photons, baryons, and dark matter during this time? What does the light that escaped this primordial prison tell us about the universe's earliest secrets? To fully appreciate the depth of the Photon Epoch, it is crucial to explore the extraordinary interplay of temperature, density, and energy scales during this period. The temperature of the universe during the Photon Epoch was staggeringly high, around 3000 Kelvin at the time of recombination. At such extreme temperatures, the universe was like a cauldron of energy, where photons, electrons, and protons engaged in constant, high-speed collisions. But as the universe expanded, this temperature gradually decreased, leading to the critical moment of recombination. Recombination is the name given to the process where free electrons combined with protons to form neutral hydrogen atoms. This might seem like a straightforward chemical reaction, but it was a pivotal event that allowed photons to decouple from matter. Before this event, photons were scattered continuously by free electrons in the plasma, preventing them from traveling long distances. Once neutral hydrogen formed, the photons were free to traverse the cosmos uninterrupted, creating the cosmic microwave background. The physics of recombination is surprisingly intricate. The process was not instantaneous but rather unfolded over a finite period of time, creating a thickness to the last scattering surface. This thickness reflects the gradual decrease in the universe's opacity as more and more electrons bound themselves into hydrogen atoms. This subtlety is crucial because it slightly blurs the fine details of the cosmic microwave background, leaving imprints that scientists can analyze to gain insights into the universe's conditions during this era. Moreover, recombination was influenced by the presence of helium, which was formed during an even earlier epoch known as Big Bang nucleosynthesis. Helium atoms also captured free electrons during recombination, contributing to the overall opacity of the universe and slightly altering the timing of the process. By studying these details, scientists can extract information about the early universe's composition, including the relative abundances of hydrogen and helium. Another fascinating aspect of the Photon Epoch is its connection to the concept of optical depth. Optical depth is a measure of how opaque the universe was to photons at a given time. During the Photon Epoch, the optical depth was extremely high, meaning photons could only travel short distances before being scattered. However, as the universe expanded and recombination occurred, the optical depth dropped dramatically, allowing photons to escape. By measuring the optical depth of the universe today, scientists can trace the history of cosmic ionization and gain insights into the first stars and galaxies that reionized the universe hundreds of millions of years later. The transition from an opaque to a transparent universe was not just a physical transformation, it was also a transition in the types of signals we can observe. The cosmic microwave background represents the limit of what we can see with light. Beyond this point, the universe was opaque, and photons carry no information from earlier times. However, other messengers, such as neutrinos and gravitational waves, can penetrate this cosmic veil, offering glimpses into the universe's earliest moments. For example, the cosmic neutrino background is thought to have decoupled from matter even earlier than the CMB, during a period known as the neutrino decoupling epoch. These relic neutrinos are extraordinarily faint, making them incredibly challenging to detect. Nevertheless, their discovery would provide a direct window into the conditions of the universe just 1 second after the Big Bang, revealing details about the interactions of particles and forces during this critical period. Similarly, primordial gravitational waves, produced during the inflationary era, could carry information from a time even earlier than the Photon Epoch. These waves would leave a unique signature in the polarization of the cosmic microwave background, known as the B-mode polarization. Detecting this signal would be a monumental achievement, providing direct evidence for inflation and offering insights into the physics of the early universe at energy scales far beyond what can be achieved in terrestrial experiments. The Photon Epoch also invites us to reconsider the concept of time itself. During this era, the universe was dominated by radiation, which behaves very differently from matter. Radiation exerts pressure, creating a dynamic interplay between gravity and expansion. This interplay determines the universe's rate of growth and sets the stage for the transition to a matter-dominated era. Understanding these dynamics requires not just observational data but also sophisticated theoretical models that incorporate the effects of general relativity, quantum mechanics, and thermodynamics. These models reveal that the Photon Epoch was a period of delicate balance. Small changes in the universe's initial conditions could have led to vastly different outcomes. For instance, if the density of dark matter had been slightly higher or lower, it would have affected the growth of density fluctuations in the photon-baryon plasma, altering the universe's large-scale structure. Similarly, variations in the density of dark energy could have changed the rate of cosmic expansion, affecting the timing of recombination and the resulting cosmic microwave background. The precision of modern cosmology allows us to test these models with astonishing accuracy. For example, the Planck satellite, which mapped the cosmic microwave background with unprecedented detail, provided measurements of the universe's age, composition, and expansion rate that are accurate to within a fraction of a percent. These measurements have not only confirmed the predictions of the lambda CDM model, which describes the universe's evolution from the Big Bang to the present, but also highlighted areas where new physics might be hiding. One of the most intriguing puzzles emerging from these studies is the so-called Hubble tension. This refers to the discrepancy between the value of the Hubble constant, which measures the universe's expansion rate, as determined from the cosmic microwave background and as measured using nearby galaxies. While the difference might seem small, it could point to new physics that modifies our understanding of the universe's evolution during the Photon Epoch, or even earlier. The Photon Epoch, therefore, is not just a chapter in the universe's history, it is a lens through which we can examine the fundamental laws of nature. It challenges us to think about the universe in ways that stretch our imagination and push the boundaries of our knowledge. It reminds us that the light we see in the sky is more than just a source of illumination. It is a record of the universe's story, a story that continues to unfold with every new discovery. As we contemplate the Photon Epoch and its legacy, we are reminded of the profound interconnectedness of all things. The photons that decoupled from matter during this epoch have traveled billions of years to reach us, carrying with them the secrets of the universe's birth. They are a testament to the power of light, not just as a physical phenomenon, but as a symbol of knowledge and discovery. The Photon Epoch also invites profound questions about the relationship between energy, matter, and structure in the universe. This was a time when the forces that govern our cosmos were locked in an intricate dance, shaping the universe as we know it today. To truly understand this era, we must examine not only the events of the epoch itself but also the conditions that preceded it and the phenomena that followed. Before the Photon Epoch, the universe was dominated by a period of nucleosynthesis, where light elements such as hydrogen, helium, and trace amounts of lithium formed. These elements would later play a critical role during recombination, as they became the building blocks for the first atoms. The precise ratios of these elements, determined during this earlier phase, are consistent across the cosmos, providing a fingerprint of the Big Bang. Studying these abundances gives us insight into the conditions of the universe at just a few minutes old. As the universe cooled and transitioned into the Photon Epoch, the interplay between photons and matter became the dominant feature. The photon baryon plasma that filled the universe was not uniform. It exhibited tiny fluctuations in density. These fluctuations were caused by quantum variations during the inflationary period and were magnified as the universe expanded. Over time, they created sound waves in the plasma, known as baryon acoustic oscillations. These oscillations are imprinted on the cosmic microwave background as faint ripples, providing a snapshot of the universe at the time of recombination. The study of these oscillations has profound implications for cosmology. By analyzing their patterns, scientists can measure the universe's geometry and determine whether it is flat, open, or closed. Current observations suggest that the universe is remarkably flat, a finding that aligns with predictions from the inflationary model. However, these ripples also carry information about the density and composition of the universe, including the mysterious components of dark matter and dark energy. The cosmic microwave background itself is a treasure trove of information. Its faint glow, with a temperature of just 2.7 Kelvin, represents the cooled remnant of the light that first escaped during the Photon Epoch. This light is remarkably uniform across the sky, but minute temperature differences reveal a wealth of information. These differences, known as anisotropies, are the imprints of the early universe's density fluctuations. Analyzing these anisotropies has led to groundbreaking discoveries. For example, the slight polarization of the cosmic microwave background light has provided evidence for the effects of primordial gravitational waves. These waves, generated during the inflationary era, ripple through space-time itself. Detecting their influence in the CMB's polarization patterns would not only confirm the theory of inflation but also offer insights into the universe's earliest moments, a mere fraction of a second after the Big Bang. In addition to polarization, the CMB reveals clues about the universe's dark components. Dark matter, which interacts primarily through gravity, influenced the growth of density fluctuations during the Photon Epoch. Its presence amplified the peaks and troughs of the baryon acoustic oscillations, leaving distinct signatures in the CMB. Meanwhile, dark energy, responsible for the accelerated expansion of the universe, affects the overall scale of these fluctuations. By studying the CMB in conjunction with large-scale galaxy surveys, scientists have pieced together a picture of a universe dominated by dark matter and dark energy. The Photon Epoch also set the stage for the formation of the first structures in the universe. The density fluctuations that we observe in the CMB grew under the influence of gravity, eventually collapsing to form the first stars and galaxies. These structures, in turn, reionized the universe, breaking apart the neutral hydrogen formed during recombination. This reionization era, which occurred hundreds of millions of years later, left its own mark on the universe, modifying the light from distant quasars and galaxies. The connection between the Photon Epoch and the later stages of cosmic evolution underscores the interconnectedness of the universe's history. Every event, from the tiniest quantum fluctuation to the formation of galaxy clusters, is part of a continuum that began with the Big Bang. By studying the Photon Epoch, we are not just learning about the past, we are also uncovering the processes that govern the universe today. What makes the Photon Epoch particularly fascinating is its accessibility to observation. Unlike earlier epochs, which remain hidden behind the cosmic veil, the Photon Epoch left behind a clear and persistent signal. The cosmic microwave background is a relic of this era, and its study has become one of the most precise and well-developed areas of cosmology. Yet, despite its richness, there is still much we do not understand. For instance, the exact nature of dark matter remains one of the most pressing questions in physics. While its gravitational effects are evident in the CMB and in the formation of large-scale structures, its composition remains elusive. Is it made of weakly interacting particles, as many theories suggest, or could it be something more exotic, like primordial black holes or sterile neutrinos? The Photon Epoch holds the key to answering these questions, as the behavior of dark matter during this time influenced the evolution of the universe in ways we can still observe today. Similarly, the nature of dark energy remains a profound mystery. While its effects on the universe's expansion became dominant long after the Photon Epoch, understanding its origins requires delving into the physics of the early universe. Could dark energy be connected to the vacuum energy predicted by quantum field theory, or does it represent an entirely new aspect of the cosmos? The answers to these questions could revolutionize our understanding of the universe's fundamental structure. The Photon Epoch also raises philosophical questions about the nature of observation and measurement. The cosmic microwave background represents the farthest we can see with light, yet it is not the end of the story. Other messengers, like neutrinos and gravitational waves, can carry information from even earlier times. However, detecting these signals is an extraordinary challenge, requiring technologies and insights that are still in their infancy. Despite these challenges, the pursuit of knowledge about the Photon Epoch is a testament to human curiosity and ingenuity. It shows how far we have come in our understanding of the universe. It also highlights the importance of collaboration, as discoveries in cosmology often require the combined efforts of scientists, engineers, and thinkers from around the world. The Photon Epoch is a reminder that the universe is not static but dynamic, constantly evolving and transforming. It invites us to think about our place in this grand cosmic narrative and to marvel at the fact that we can even ask these questions. The photons that escaped during this epoch have traveled billions of years to reach us, carrying with them a message of light and knowledge. As we continue to study this era, we are not just looking into the past. We are also paving the way for future discoveries that will deepen our understanding of the cosmos and our place within it. The legacy of the Photon Epoch resonates throughout modern cosmology. It represents a foundational period that bridged the chaotic, high-energy infancy of the universe with the structured and evolving cosmos we observe today. The intricate interactions of photons, baryons, and dark matter during this time played a crucial role in shaping the universe's architecture, from the vast cosmic web to the stars and galaxies that now populate the sky. One of the most remarkable aspects of the Photon Epoch is its role in demonstrating the unity of the fundamental forces of nature. During the universe's earliest moments, the forces we know today, gravity, electromagnetism, and the strong and weak nuclear forces, were unified in a single framework. As the universe cooled and expanded, these forces separated, or broke symmetry, to take on the distinct roles we observe today. The Photon Epoch serves as a transitional period where electromagnetic interactions dominated, highlighting the profound relationship between light and matter. This era also provides a unique testing ground for the laws of physics. The extreme conditions of the early universe, high temperatures, immense pressures, and rapid expansion, created an environment unlike anything we can replicate on Earth. By studying the photon-baryon plasma and the resulting cosmic microwave background, scientists can test theories of particle physics and cosmology with unprecedented precision. For instance, discrepancies in the measured value of the Hubble constant, an important parameter describing the universe's expansion rate, may point to new physics beyond the standard model. The Photon Epoch's relevance extends beyond theoretical physics into practical implications for understanding the universe's evolution. The density fluctuations imprinted during this time are the seeds of all cosmic structure. Without them, the universe would remain a featureless expanse of evenly distributed matter and energy. These initial perturbations grew under the influence of gravity, eventually forming the intricate patterns of galaxies, clusters, and superclusters we observe today. The study of these fluctuations has also inspired advancements in other fields, including algorithms for data analysis and simulations. Yet, the Photon Epoch is not merely a story of light and matter. It is also a story of time. The era's events unfold over hundreds of thousands of years, with each moment contributing to the universe's larger narrative. This passage of time is both a reminder of the vast scales of cosmic history and an invitation to consider the connections between the past, present, and future. In the same way that photons from this epoch continue to travel through space, the knowledge we gain from studying them reverberates through our understanding of existence. As scientists probe deeper into this era, new mysteries emerge. For example, while we understand the basics of recombination and the formation of the cosmic microwave background, there are still unanswered questions about the exact mechanisms that govern the interaction between photons and matter. What were the precise conditions that led to the decoupling of light from the plasma? How did quantum effects influence the macroscopic properties of the early universe? These questions are at the forefront of cosmological research, driving the development of more sensitive instruments and innovative theories. One exciting avenue of exploration involves primordial gravitational waves. Unlike electromagnetic radiation, gravitational waves can pass through the dense plasma of the early universe without scattering. Detecting these waves could provide a direct glimpse into the moments before the Photon Epoch, revealing insights into the inflationary period and the origins of space-time itself. Experiments like LIGO, Laser Interferometer Gravitational Wave Observatory, and future missions such as the Laser Interferometer Space Antenna, LISA, aim to uncover these faint signals, offering a new window into the cosmos. The Photon Epoch also has implications for the search for life beyond Earth. By understanding the conditions that led to the formation of the first atoms, stars, and galaxies, scientists can better determine the factors that contribute to habitable environments. The distribution of matter during this epoch influenced the locations where stars and planetary systems could form, setting the stage for the potential emergence of life. Studying this period may ultimately help us answer one of humanity's most profound questions: are we alone in the universe? As we contemplate the Photon Epoch, it is worth considering its philosophical implications. This era reminds us of the interconnectedness of all things, from the tiniest particles to the largest structures in the cosmos. It highlights the beauty and complexity of a universe governed by simple, elegant laws. And it challenges us to think about the nature of knowledge itself, how we can infer so much about a time billions of years in the past using only the faint traces of ancient light. In many ways, the Photon Epoch represents the triumph of human curiosity and ingenuity. The story of this era is one of discovery, resilience, and the relentless pursuit of understanding. It shows that even in the face of immense complexity, we can uncover the secrets of the cosmos by asking the right questions and seeking the right answers. As we look to the future, the study of the Photon Epoch will continue to inspire new generations of scientists and thinkers. Its lessons will shape our understanding of the universe, guiding us toward deeper insights and new frontiers. In the end, the light from this epoch is more than just a relic of the past. It is a beacon for the future, illuminating the path to discovery and exploration. The legacy of the Photon Epoch extends beyond the realm of physics, influencing our understanding of existence itself. This era offers a unique lens through which we can explore the origins of the universe and our place within it. By delving deeper into this period, we gain not only scientific insights but also a sense of awe for the intricate tapestry of creation. One fascinating aspect of the Photon Epoch is its connection to the Anthropic principle, the idea that the universe's physical constants are finely tuned to allow for the existence of life. The interactions between photons and matter during this era set the stage for the emergence of chemical elements, stars, and galaxies. Without the precise balance of forces and conditions, the universe might have evolved in a way that precluded the possibility of life. This raises profound questions about the nature of reality and the mechanisms that led to such fine-tuning. Are these conditions the result of chance, necessity, or something beyond our current understanding? The Photon Epoch also challenges our perception of time. In our daily lives, time is linear and segmented into minutes, hours, and days. However, during this early period, time was intrinsically tied to the universe's expansion and cooling. Each second saw dramatic changes in temperature, density, and energy levels. To truly grasp the Photon Epoch, we must think in terms of cosmological time scales, an exercise that pushes the boundaries of human imagination. This shift in perspective can be both humbling and enlightening, reminding us of the vastness of the cosmos and our relatively small place within it. Another intriguing element of the Photon Epoch is its role in the cosmic narrative of symmetry and asymmetry. At the universe's inception, matter and antimatter were created in nearly equal amounts. Yet, for reasons still not fully understood, matter slightly outnumbered antimatter. This tiny imbalance allowed matter to dominate, giving rise to the stars, planets, and life we see today. The Photon Epoch provides critical clues about this asymmetry, as the interactions between photons and particles were directly influenced by the slight excess of matter. Understanding this phenomenon could unlock new insights into the fundamental nature of reality and the origins of the universe. The Photon Epoch also underscores the importance of collaboration in scientific discovery. The study of this era requires expertise from multiple disciplines, including astrophysics, particle physics, and mathematics. It also relies on advanced technology, such as space-based telescopes and particle accelerators, to gather and analyze data. This collaborative approach mirrors the interconnected nature of the universe itself, where every particle, wave, and force plays a role in shaping the cosmos. By working together, scientists can piece together the puzzle of the Photon Epoch, uncovering the story of our universe's early days. In addition to its scientific and philosophical significance, the Photon Epoch has inspired countless works of art, literature, and popular culture. The image of a universe filled with seething plasma and trapped light evokes a sense of mystery and wonder, serving as a metaphor for the hidden complexities of existence. This era reminds us that even in the most chaotic and turbulent times, there is beauty and order waiting to be discovered. Looking forward, the study of the Photon Epoch holds immense promise for future discoveries. As technology advances, scientists will be able to probe this era with greater precision, uncovering new details about the universe's infancy. For example, next-generation telescopes like the James Webb Space Telescope, JWST, and future missions to map the cosmic microwave background will provide unprecedented insights into this critical period. These efforts will deepen our understanding of the universe and may even lead to breakthroughs in other fields, such as quantum mechanics and the search for extraterrestrial life. The Photon Epoch also serves as a reminder of the power of light as a tool for exploration. From the ancient starlight captured by telescopes to the photons that illuminate our daily lives, light is a constant source of knowledge and inspiration. By studying the light from the early universe, we can connect with a time billions of years in the past, bridging the gap between then and now. This connection highlights the continuity of existence and the enduring legacy of the universe's earliest moments. Ultimately, the Photon Epoch is more than just a chapter in the history of the universe. It is a testament to the resilience of matter and energy, the elegance of natural laws, and the boundless curiosity of humanity. As we continue to unravel the mysteries of this era, we are reminded of the profound interconnectedness of all things, from the photons that shape the cosmos to the thoughts and questions that drive our exploration. The story of the Photon Epoch is, in many ways, the story of us all. The Photon Epoch is a profound bridge between the incomprehensible chaos of the universe's first few seconds and the more familiar cosmos we observe today. It captures a time when the universe was young, hot, and alive with interactions that determined its ultimate fate. Every photon, quark, and gluon that existed during this time was intricately woven into a tapestry of high-energy physics that would eventually cool into the universe's recognizable form. To understand this epoch is to understand the seeds of cosmic evolution, a tale that began in searing plasma and ended with the first light of the stars. The cosmic microwave background (CMB) is the silent witness to this epoch, a snapshot frozen in time. The CMB, which fills the universe even now, is the oldest light we can observe, traveling unimpeded since the moment it was released. But during the Photon Epoch, this light was far from free. Trapped in a dense plasma, photons constantly scattered off charged particles like electrons and protons, unable to travel far before colliding. This created an opaque universe, where light could not escape the relentless tug-of-war between radiation and matter. This interplay between photons and particles was governed by fundamental physical laws, which are surprisingly accessible to us today. The interaction of photons with electrons, for instance, is described by quantum electrodynamics, one of the most precise theories in physics. By modeling these interactions in computer simulations, scientists can recreate the conditions of the Photon Epoch with astonishing detail, testing our understanding of the universe's fundamental forces. During this time, photons didn't merely scatter, they carried with them crucial information about the density and temperature of the plasma. These variations in density were slight, fluctuations of just 1 part in 100,000, but they were enough to imprint a pattern onto the photons. This pattern would later manifest as the tiny temperature variations in the CMB that cosmologists measure today. These seemingly insignificant variations are the fingerprints of the universe's earliest moments, containing clues about everything from the nature of dark matter to the physics of cosmic inflation. The physics of the photon epoch also has profound implications for the concept of thermal equilibrium. At the height of this epoch, the universe was nearly in perfect thermal balance. Photons and particles exchanged energy so rapidly that the entire cosmos could be described by a single temperature. This uniformity is why the CMB appears almost identical in every direction, a phenomenon known as isotropy. Yet, the tiny fluctuations in this equilibrium are what make the universe interesting. They are the seeds of all structure, from galaxies to galaxy clusters. These fluctuations didn't arise randomly. They are thought to have originated during an even earlier period known as inflation, a time when the universe expanded exponentially in a fraction of a second. The rapid stretching of space during inflation amplified quantum fluctuations, spreading them across the cosmos. By the time of the photon epoch, these fluctuations were etched into the plasma, shaping the distribution of matter and energy. The fact that we can detect these imprints billions of years later speaks to the extraordinary power of physics to connect the microscopic and the cosmic. The end of the photon epoch was marked by a dramatic shift, the era of recombination. Around 380,000 years after the Big Bang, the universe had cooled sufficiently for electrons and protons to combine into neutral hydrogen atoms. With fewer free electrons to scatter them, photons could finally travel freely, marking the universe's transition from opaque to transparent. This is the moment captured by the CMB, a relic of the very first light to shine across the cosmos. Recombination was not just a turning point for light, it was also the beginning of structure formation. With photons no longer exerting as much pressure on the plasma, gravity could take over, pulling matter together to form the first clouds of gas. These clouds would eventually collapse under their own weight, igniting nuclear fusion and giving birth to the first stars. Thus, the photon epoch set the stage for the universe's next act, the age of stars and galaxies. The study of this epoch has become a cornerstone of modern cosmology, driving technological advancements and theoretical breakthroughs. Instruments like the Planck satellite have provided detailed maps of the CMB, revealing not just its temperature but its polarization, a subtle effect caused by the scattering of photons during the photon epoch. These measurements allow scientists to test hypotheses about everything from the properties of neutrinos to the shape of the universe itself. The photon epoch also serves as a reminder of the interconnectedness of all things. The photons released at the end of this epoch are the same ones that now fill every corner of the cosmos. They are a constant presence, a silent witness to the universe's history. In a very real sense, these ancient particles of light connect us to the earliest moments of creation, a bridge between the distant past and the present. As we continue to explore the photon epoch, new questions arise. Could there be unknown particles or forces that influence this era? How did the universe transition so seamlessly from chaos to order? And what can this epoch teach us about the ultimate fate of the cosmos? These questions drive the ongoing quest to understand not just the photon epoch, but the broader narrative of existence. The photon epoch is more than just a chapter in cosmic history, it is a key to understanding the universe itself. It is a story of light trapped and light freed, of chaos giving way to structure, of the profound interplay between matter and energy. In studying this epoch, we are not merely looking back in time, we are uncovering the very foundations of reality, a journey that continues to inspire and astonish. The photon epoch continues to hold an almost mystical allure for scientists and curious minds alike. The time before light could escape is, in many ways, a period of absolute transformation, an era where the fundamental forces were still in the process of balancing, and the universe was a chaotic, dense soup of particles. But that soup was also the birthplace of everything we know, the blueprint of galaxies, stars, and all matter. To truly appreciate the magnitude of this period, it's essential to step back and consider the role of photons themselves. Photons are not like ordinary particles we encounter every day. They are quanta of light, fundamental particles that travel at the speed of light and carry electromagnetic radiation. But in the photon epoch, photons were not free. They were constantly interacting with the dense, hot plasma around them. This interplay kept them from doing what they do best: travel across the cosmos unimpeded. When we talk about the cosmic photon sea, during this time, we are referring to a universe teeming with light that could not yet escape its constraints. The photons were in constant collision with free electrons and protons. Every time a photon collided with a free electron, it was scattered in a process known as Thomson's scattering. Because of this constant scattering, the universe was effectively opaque. The photons were trapped in the cosmic fog, unable to move freely through space. This dense environment, with photons bouncing around constantly, is also a key to understanding the homogeneity of the early universe. The temperature and density of the universe were nearly uniform at this time, and this homogeneity has been preserved in the cosmic microwave background radiation, CMB, which carries the signature of those very early conditions. The CMB is the oldest and most direct evidence we have of the photon epoch. The CMB itself tells us about the temperature of the universe at that time, which was roughly 3000 Kelvin. This temperature is crucial because it marks the point at which the plasma could cool enough for electrons and protons to combine into neutral hydrogen atoms, an event known as recombination. Once this happened, photons were no longer scattered by free electrons, and they were free to travel across the universe, marking the end of the photon epoch and the birth of the transparent universe we see today. But it's the role that these photons played in the very structure of the universe that stands out. The temperature fluctuations captured in the CMB, caused by the tiny density differences in the early plasma, became the seed for the formation of galaxies and large-scale structures. These fluctuations, measuring just 1 part in 100,000, are not just minor imperfections. They represent the very fabric of the universe, encoding vital information about how matter would evolve over billions of years. Scientists can read these subtle variations like a map to the earliest structure of the cosmos. The significance of this is not just academic, it has far-reaching implications for our understanding of physics. In particular, the study of the photon epoch links back to questions of fundamental physics that have occupied theorists for centuries. One of the central questions is the nature of dark matter. Dark matter, which makes up roughly 27% of the universe's mass-energy content, has been elusive, as it does not interact with light in any way that we can detect. However, its gravitational influence on galaxies is profound. The photon epoch's intense conditions and the subsequent interactions between photons and matter help us understand how dark matter might have influenced the evolution of the early universe. In addition to dark matter, there is also dark energy to consider. Dark energy is even more mysterious, accounting for roughly 68% of the universe's total energy content. It is believed to be responsible for the accelerated expansion of the universe. The photon epoch provides key insights into the early dynamics of the universe, laying the groundwork for understanding how forces like dark energy could shape the cosmos at large. By studying the photon epoch, we also get a glimpse into the very nature of space itself. Space, as we understand it today, is a vast and expanding void. But during the photon epoch, space was more akin to a dense, energetic fluid, one that expanded and cooled rapidly. The rapid expansion we associate with cosmic inflation happened just before this epoch, during a period that is still shrouded in mystery. The connection between inflation and the photon epoch is crucial because inflation helped set up the physical conditions that made the photon epoch, and the universe as we know it, possible. As the universe expanded, the temperature dropped and the photons were finally freed from their cosmic prison. But by the time they were able to travel freely, the universe had already undergone massive changes. This transformation wasn't just about temperature. It was about the very fabric of the universe itself. In the aftermath of the photon epoch, gravity began to play an increasingly important role, pulling matter together into the first clumps that would form the first stars and galaxies. Looking back at the photon epoch, It's amazing to realize how much it set in motion. All the forces that would govern the evolution of the universe, gravity, electromagnetism, and the nuclear forces, were already at work, but they were still in the process of setting up the stage for the more complex interactions that would unfold. The Photon Epoch was a crucial part of this intricate setup, a time when the laws of physics were defining the rules by which the universe would grow and evolve. But what happens next? As the universe continued to expand and cool after the Photon Epoch, the first stars began to form. The universe entered the era known as the Cosmic Dark Ages, before the first galaxies lit up. These first stars, born from the primordial hydrogen gas that formed during recombination, ignited the next phase in cosmic evolution. The universe began to transition from a dark, featureless place into a vibrant expanse filled with light, radiation, and the building blocks of life. The study of the Photon Epoch has shown us that we are not simply the descendants of stars, but the heirs to an entire cosmos of interaction, radiation, and physics stretching back to the very dawn of time itself. As we continue to refine our understanding of the Photon Epoch, it raises profound questions. How do we connect the era of photons to the more familiar universe we live in today? What can the cosmic microwave background teach us about the forces that governed the early universe? How can we continue to probe the deepest mysteries of the cosmos? Each new discovery builds upon the last, providing deeper insight into the nature of the universe and its origins. As our technology improves and our understanding of physics evolves, we will undoubtedly learn more about this pivotal period in the history of the universe. Whether it's through more advanced telescopes, particle accelerators, or novel theoretical models, the Photon Epoch will remain a central focus of cosmology for years to come. The Photon Epoch serves as both a time capsule and a challenge. It offers us a glimpse of the universe's earliest moments, but also presents us with questions that continue to drive scientific inquiry and our deeper understanding of the cosmos. Through the study of this era, we are not only uncovering the past, we are shaping the future of science, philosophy, and our place in the vast expanse of space. The Photon Epoch serves as a reminder that the universe we know is but the tip of an iceberg. Beneath the surface lies an entire cosmic history filled with processes, transformations, and forces that have shaped the very fabric of our existence. The era when photons were trapped in a dense plasma is one such chapter in this story, but it's a chapter that holds the key to understanding many of the fundamental forces and phenomena we encounter today. One of the most fascinating aspects of the Photon Epoch is how it links directly to the phenomenon known as cosmic inflation. This rapid expansion of the universe occurred just before the Photon Epoch, during a fraction of a second after the Big Bang. In that brief moment, the universe expanded exponentially, stretching from subatomic scales to vast stretches in the blink of an eye. The theory of inflation helps explain the uniformity and homogeneity observed in the cosmic microwave background radiation. But while inflation set the stage for the Photon Epoch, the aftermath of this period helped cement the structure of the universe. As photons, along with other particles, interacted and scattered within the hot plasma, the universe was essentially an energy-filled sea. Everything was in constant motion, not just particles but also the very fabric of space-time itself. This energetic chaos marked a time when our universe was not just expanding, it was brewing. As the photons traveled through this soup of particles, they were constantly scattered by free electrons and protons, preventing them from traveling in straight lines. This scattering is known as Thomson scattering, and it helped to shape the universe's properties. For instance, it contributed to the fact that the universe was opaque for about the first 380,000 years. Photons had to wait for the universe to cool enough for recombination to take place, an event where protons and electrons combined to form neutral hydrogen atoms. Once that happened, the universe went from being opaque to transparent, allowing light to travel freely across vast distances for the first time in history. This moment of transparency marked a significant turning point in the evolution of the cosmos. It's when the first light began its long journey through space, eventually reaching us as the cosmic microwave background radiation we study today. This afterglow is more than just a relic of the past, it's a key piece of the puzzle that helps scientists understand how the universe has evolved, how matter came together to form stars and galaxies, and how the fundamental laws of physics have played out across the cosmos. The cosmic microwave background radiation is the oldest and most direct signal we have of the early universe, carrying information from the time when the universe was only about 380,000 years old. But even as we study the CMB, we continue to look deeper. By analyzing the small variations in temperature found in the CMB, scientists have been able to trace the seeds of galaxy formation, identifying the very fluctuations in density that led to the large-scale structures we see today. These fluctuations, while minuscule, were the starting point of everything: galaxies, stars, and even the formation of clusters of galaxies. But why does all this matter? The study of the photon epoch and the cosmic microwave background offers a window into the very nature of space-time. It shows how tiny changes in the early universe can cascade into the vast complexity of the cosmos. It also offers a clue as to why the universe is structured the way it is. Understanding the photon epoch and its aftermath is critical for answering fundamental questions about the universe's origins, its large-scale structure, and its ultimate fate. One of the most critical mysteries that scientists continue to investigate is the exact nature of dark matter and dark energy, two components that together make up most of the universe's mass-energy content. While these forces remain invisible to direct observation, their influence is undeniable. Dark matter, which interacts gravitationally but not electromagnetically, has been implicated in the formation of galaxies and clusters. By studying the early conditions of the photon epoch and the cosmic microwave background, we gain insights into how these elusive forces may have played a role in shaping the universe's large-scale structure. Dark energy, on the other hand, is the force driving the accelerated expansion of the universe. This mysterious energy constitutes roughly 68% of the universe's total energy content, and remains largely a mystery. The study of the photon epoch may provide crucial information on how dark energy came to dominate the cosmos. As we study the early universe, we begin to piece together the events that led to the present state of cosmic acceleration and the ongoing expansion of space. But let's step back and think about the broader implications of the photon epoch. Imagine a universe without light, a vast, dark expanse where even the smallest spark of radiation is caught up in a whirlwind of interactions. This time before photons could freely travel through space is not just a footnote in the history of the universe. It is a moment that helped lay the groundwork for everything that followed. Without the photon epoch, there would be no cosmic microwave background radiation, no foundation for understanding the early universe. Without this period, the formation of the first stars and galaxies might not have been possible, and the universe might not have taken the shape it did. In many ways, the photon epoch marks the dawn of the universe's modern era, a time when matter began to clump together, when light began to travel freely, and when the conditions for life were set in motion. As we continue to study this early period, it becomes clear that the photon epoch is a crucial time in the history of the cosmos. It's the birth of the universe as we know it, and every new discovery we make about this era helps us understand the very forces that govern everything, from the stars above to the fundamental particles that make up our own bodies. And yet, for all that we know, we are still just scratching the surface of understanding this period. The universe is vast, and the more we learn, the more we realize how much we don't know. The photon epoch is just one chapter, but it's one that connects to so much of what we study today. From the formation of galaxies to the nature of dark matter and dark energy, the answers to these cosmic puzzles lie buried in the remnants of the photon epoch. As we continue to explore the mysteries of the cosmos, the lessons of this early time continue to shape our understanding of everything. And as technology advances and our ability to observe deeper into the universe improves, we can be certain that the photon epoch will remain a crucial part of the story of the universe, one that will continue to fuel our curiosity and drive our quest for knowledge about the cosmos and our place in it. The more we dive into the photon epoch, the more we realize how fundamental it is to understanding the very nature of our universe. It's one of those periods that might seem distant and removed from our day-to-day lives, but it's actually at the very core of the universe's structure and evolution. Without it, the universe we observe today wouldn't be as we know it. From the formation of galaxies to the emergence of stars, all of these fundamental processes are tied to the conditions set by the photon epoch. As the universe cooled and the matter began to settle, the forces that we take for granted today, gravity, electromagnetism, and the strong and weak nuclear forces, continued to shape the cosmos. What followed this dense soup of plasma and particles was the formation of the first neutral atoms. This process, known as recombination, was a critical moment in cosmic history. It marked the point when the universe was finally able to undergo a significant transformation, allowing the first photons to escape from the dense plasma that had previously kept them trapped. Before recombination, the universe was a hot, opaque soup of particles that couldn't allow light to pass through. The photons were constantly scattering off free electrons and protons, making it impossible for them to travel freely. But once the universe cooled enough, the protons and electrons could combine to form neutral hydrogen atoms. This process was a game-changer. It allowed photons to finally move freely, unimpeded by the dense plasma that had once trapped them. This moment of release is what allowed light to travel across vast stretches of space, marking the end of the photon epoch. This sudden transparency of the universe is known as the decoupling of photons from matter, and it's the point at which the cosmic microwave background, CMB, was born. The CMB is a faint glow of radiation that fills the entire universe and provides us with a snapshot of the universe when it was just 380,000 years old. The discovery of the CMB was one of the most significant breakthroughs in cosmology, as it provided direct evidence for the Big Bang theory, and allowed us to peer back in time to when the universe was still young and forming. The photons that make up the cosmic microwave background are like messengers from the past. They carry information about the early universe, telling us about its temperature, density, and even the distribution of matter and energy. By studying the CMB, scientists have been able to trace the origins of galaxies, clusters of galaxies, and even the vast cosmic voids that exist between them. These tiny fluctuations in the temperature of the CMB are the seeds from which the universe grew into the vast, complex structure we see today. In fact, it's these fluctuations that are believed to have played a pivotal role in the formation of galaxies and other large-scale structures. These fluctuations were caused by the distribution of matter in the early universe, and they ultimately led to the clumping of matter into the stars and galaxies we observe. In this sense, the photon epoch wasn't just a period of transition, it was also a crucial moment in the creation of the universe's architecture. Yet even as we celebrate our discoveries about the early universe, there are still so many unanswered questions. While the photon epoch gave us the first light of the cosmos, it also revealed how much we still don't understand about the universe's origins. The exact nature of dark matter and dark energy, two mysterious components of the universe that make up the vast majority of its mass-energy content, remains one of the most pressing questions in cosmology today. Dark matter, which doesn't emit or interact with light in any way, is thought to make up about 27% of the universe. It's invisible to our instruments, yet we know it exists because of its gravitational effects on visible matter. Dark energy, on the other hand, is the mysterious force that's causing the accelerated expansion of the universe. It's believed to account for roughly 68% of the universe's energy content. Together, dark matter and dark energy form the majority of the universe's mass-energy budget, but their exact properties remain elusive. One of the most exciting aspects of the photon epoch is that it may hold clues to the nature of these dark components. By studying the fluctuations in the cosmic microwave background, scientists hope to gain a better understanding of how dark matter and dark energy shaped the early universe. These fluctuations, though tiny, carry with them information about the forces that govern the universe's evolution. And as we continue to study the CMB with ever more advanced technology, we may be able to uncover the secrets of these mysterious components. The study of the photon epoch also plays a key role in understanding the fate of the universe. The way the universe expanded after the photon epoch has profound implications for its future. We know that the universe has been expanding ever since the Big Bang, but the rate of that expansion is not constant. The discovery that the universe's expansion is accelerating has led scientists to propose a variety of theories about the ultimate fate of the cosmos. Will the universe continue expanding indefinitely, eventually leading to a big freeze, where everything becomes so spread out that stars and galaxies fade into the darkness? Or will gravity eventually slow down the expansion, causing the universe to collapse in on itself in a big crunch? Or is there some other fate awaiting the universe, perhaps one that we have yet to imagine? These questions may seem far removed from the Photon Epoch, but in reality, they are deeply connected. The early universe's conditions, as shaped by the Photon Epoch, helped determine how the universe expanded in the first place. And understanding the forces that govern that expansion will help us understand what might happen to the universe in the future. For all of the breakthroughs we've made in understanding the Photon Epoch, there's still so much we don't know. The more we study the early universe, the more we realize how much we have yet to uncover. With new technologies and methods of observation on the horizon, we're only beginning to scratch the surface of what the Photon Epoch can tell us about the cosmos. It's one of the most exciting times to be studying cosmology, as we stand on the threshold of discoveries that could change everything we know about the universe. The Photon Epoch, which was once a distant and mysterious period, is now at the heart of our quest to understand the origins, structure, and future of the cosmos. And as we continue to explore the mysteries of the early universe, we are bound to uncover new truths that will challenge our understanding of the very nature of reality itself. As we continue to unravel the mysteries of the Photon Epoch, it's important to also consider how the universe evolved after the release of the cosmic microwave background, CMB, and how those processes laid the groundwork for everything we observe today. The decoupling of photons from matter was not the end of the story but rather a critical chapter that set the stage for the formation of the universe's more complex structures. Once the photons were no longer trapped by the dense plasma, the universe entered what is often referred to as the cosmic dark ages. This period lasted for hundreds of millions of years, during which the universe remained a dark and seemingly empty place. However, it was not truly empty. It was a vast, expanding expanse filled with hydrogen and helium gas. The gas was still too diffuse to form stars or galaxies, but it was the fuel for the coming cosmic renaissance. During these dark ages, the first stars, known as population 3 stars, began to form. These stars were different from the stars we see today. They were composed almost entirely of hydrogen and helium, with virtually no heavier elements like carbon, oxygen, or iron. These first stars were massive, hot, and short-lived, burning through their fuel at a rapid pace. Their formation marked the end of the Dark Ages and the beginning of a new era in cosmic history, the era of reionization. Reionization is the process through which the first stars and galaxies emitted intense ultraviolet radiation, which ionized the hydrogen gas that had once been neutral. This process essentially relit the universe, making it once again transparent to light. Reionization played a critical role in shaping the structure of the universe, as it marked the transition from a dark, opaque universe to one that was filled with light and radiation. It also helped shape the large-scale structure of the universe, as the radiation from the first stars influenced the distribution of gas and matter across the cosmos. The transition from the Photon Epoch to the era of reionization was not immediate. It was a slow and gradual process that spanned millions of years. However, it is a crucial period for understanding the universe's early evolution. The light from the first stars helped illuminate the dark matter that had been present since the Photon Epoch, revealing the invisible scaffolding that would later give rise to galaxies, clusters, and the large-scale structures we see today. As the universe continued to expand and cool, the formation of galaxies began to accelerate. The small fluctuations in the density of matter that had been present since the Photon Epoch played a key role in this process. These fluctuations, caused by tiny differences in the temperature of the CMB, acted as the seeds for the formation of the first galaxies. Over time, these small density variations led to the gravitational collapse of gas and dust, eventually forming the first stars and galaxies. The Photon Epoch, by setting the conditions for the formation of the first atoms and the eventual release of light, set in motion a chain of events that led to the creation of everything we see in the universe today. The birth of stars, galaxies, and other structures was deeply influenced by the conditions created during this early phase of the universe. Understanding this period is critical to understanding not just the past of the universe, but its future as well. The study of the photon epoch and the cosmic microwave background has also given rise to new questions about the very nature of the universe. One of the most profound mysteries that has emerged in recent years is the question of dark energy. The accelerated expansion of the universe, which was discovered in the late 20th century, cannot be explained by the gravitational effects of matter alone. Instead, it suggests the presence of an unknown force, dark energy, that is driving the universe apart. Dark energy is thought to make up roughly 68% of the universe's energy content, yet its properties remain a mystery. Could the origins of dark energy be traced back to the photon epoch? Could it be connected to the way the universe expanded during the first few moments after the Big Bang? These are questions that researchers are actively investigating, using both theoretical models and observational data. The deeper we look into the early universe, the more we realize that the photon epoch was not just a passive period of cosmic history. It was a time of profound change, laying the foundation for everything that came after it. In many ways, the study of this period is the key to unlocking the ultimate secrets of the universe. The photon epoch also holds critical clues about the nature of cosmic inflation, the rapid expansion of the universe that is believed to have occurred in the moments immediately following the Big Bang. Inflation theory suggests that the universe expanded at an extraordinary rate in the first fraction of a second, stretching space-time to unimaginable scales. This expansion would have smoothed out the universe, creating a homogeneous and isotropic cosmos. The fluctuations in the CMB that we observe today are thought to be remnants of this inflationary period, providing us with a snapshot of the universe's birth. As we study the photon epoch, we begin to piece together the story of how the universe evolved from a hot, dense, and chaotic state to the vast, complex structure we see today. The photons that were trapped in the plasma during this epoch were not just passive participants. They carried with them information that has allowed us to map the early universe and uncover its most profound secrets. The research being conducted on the photon epoch is transforming our understanding of the cosmos. As new technologies allow us to probe the farthest reaches of space and time, we are beginning to uncover evidence of phenomena that were once thought to be purely theoretical. From the nature of dark matter and dark energy to the origins of cosmic inflation, the photon epoch holds the keys to some of the most profound mysteries in science. One of the most exciting aspects of studying the photon epoch is that it provides a glimpse into the very origins of the universe itself. By studying the cosmic microwave background and the tiny fluctuations that exist within it, we are essentially looking back in time to a point when the universe was just a fraction of a second old. In a sense, these ancient photons are time travelers, carrying with them the secrets of the past and offering us a unique window into the birth of everything. While we have made tremendous strides in understanding the photon epoch and its implications, there is still much we don't know. The early universe is a place of mystery, where the laws of physics as we know them were in their infancy. As we continue to explore the cosmos, it is likely that we will uncover even more surprises, new phenomena, new forces, and new insights into the nature of reality itself. But one thing is certain, the photon epoch will continue to be a cornerstone of our understanding of the universe. It was the moment when light first pierced the darkness, revealing a universe that had been hidden for so long. And as we look to the future, the study of this epoch will be essential in helping us understand where the universe came from, where it's going, and what secrets it may still be hiding. The photon epoch is not just a chapter in the story of the universe, it is the story of the universe itself, told through the lens of light. And as we continue to explore its mysteries, we are not just uncovering the past, we are unlocking the very future of our understanding of the cosmos. As we continue to probe deeper into the cosmic history and the photon epoch, it becomes clear that this brief period of time, lasting only a few 100,000 years, was not simply a transitional phase in the universe's evolution. Rather, it served as a turning point that fundamentally altered the trajectory of cosmic history. During this time, the universe underwent dramatic changes that laid the groundwork for the formation of the first atoms, stars, and galaxies. It was also during this epoch that the universe began to take on the features that we associate with the cosmos today, the vast, interconnected web of galaxies and clusters that stretches across the observable universe. While the photons were trapped in a dense plasma, their behavior was anything but simple. As the universe cooled, the electrons and protons began to combine to form neutral hydrogen atoms, which in turn allowed the photons to travel freely for the first time. This event is known as recombination, and it marked the end of the Photon Epoch. But the process was not instantaneous, and the photons that were released during this time still carry with them the imprints of the conditions in which they were formed. These imprints are encoded in the cosmic microwave background (CMB) radiation, which is often referred to as the afterglow of the Big Bang. The CMB is one of the most important tools we have for studying the early universe. By analyzing the tiny temperature fluctuations in the CMB, scientists are able to reconstruct a detailed map of the universe's infancy. These fluctuations correspond to the small density variations in the early universe that eventually grew into the galaxies and clusters of galaxies we see today. In essence, the CMB is a snapshot of the universe when it was just 380,000 years old, giving us a glimpse into a time when the cosmos was still in its infancy. These fluctuations are not just random noise. They are the fingerprints of the universe's earliest moments, offering insights into the forces that shaped the cosmos. By studying them, scientists can gain valuable information about the fundamental properties of the universe, such as its age, composition, and the nature of dark matter and dark energy. The CMB has already provided us with a wealth of knowledge, but it holds even more secrets that are waiting to be uncovered. One of the most exciting aspects of studying the CMB is that it allows us to explore the very origins of the universe itself. By analyzing the patterns of fluctuations in the CMB, scientists are able to test theories of cosmic inflation, a period of rapid expansion that occurred in the moments following the Big Bang. Inflation theory suggests that the universe expanded at an extraordinary rate, much faster than the speed of light, in a fraction of a second. This rapid expansion smoothed out the distribution of matter and energy, creating the homogeneous and isotropic universe we see today. The study of the Photon Epoch and the CMB is also helping to refine our understanding of dark matter, an elusive and mysterious substance that makes up around 27% of the universe's total mass. Dark matter does not interact with light in the same way that normal matter does, which makes it incredibly difficult to detect directly. However, its presence can be inferred from its gravitational effects on visible matter. The CMB provides indirect evidence for the existence of dark matter, as the density fluctuations observed in the early universe were influenced by the gravitational pull of dark matter. By studying these fluctuations, scientists are able to estimate the amount and distribution of dark matter in the early universe, providing valuable clues about its nature. As we look deeper into the Photon Epoch, it becomes clear that this period was more than just a precursor to the formation of stars and galaxies. It was a time when the fundamental forces of nature were still taking shape. The properties of matter, energy, and space-time were in their infancy, and the interactions between these forces set the stage for the evolution of the universe. Understanding the Photon Epoch is essential for understanding the laws that govern the cosmos. But the mysteries of the Photon Epoch don't stop there. The study of the early universe also holds profound implications for our understanding of the fundamental nature of reality. During the Photon Epoch, the universe was in a state of extreme density and temperature. Under such conditions, the laws of physics as we know them began to break down, giving rise to new, unknown phenomena. Some of these phenomena may hold the key to understanding the true nature of space-time, gravity, and the fundamental forces of the universe. One of the most intriguing questions that scientists are grappling with today is the nature of quantum gravity. The current theories of physics, including general relativity and quantum mechanics, work well in their respective domains but break down when they are combined. The quest for a theory of quantum gravity seeks to unify these two frameworks into a single theory that can explain the behavior of the universe at both the smallest and largest scales. The Photon Epoch, with its extreme conditions, may hold the key to unlocking the mysteries of quantum gravity. As we continue to study the Photon Epoch and the early universe, it's clear that there is still much we don't know. The more we uncover, the more questions arise. The Photon Epoch was just one brief moment in the history of the universe, but it is a moment that holds the answers to some of the most profound questions in science. From the origins of light and the formation of atoms to the nature of dark matter and quantum gravity, the the Photon Epoch provides us with a unique window into the birth of the universe. In the coming decades, new technologies and observations will allow us to probe even deeper into the early universe. With more advanced telescopes, like the James Webb Space Telescope, and future missions aimed at studying the CMB, we will be able to gather even more detailed data about the Photon Epoch and the conditions that existed in the first moments of the universe's existence. These advancements will undoubtedly lead to new discoveries that will reshape our understanding of the cosmos. The Photon Epoch is not just an isolated event in the universe's history, it is the foundation upon which the entire structure of the universe was built. It set the stage for the formation of stars, galaxies, and all the cosmic structures that came after. And as we continue to explore the depths of space and time, the Photon Epoch will remain a key chapter in the story of the universe, offering us insights into the fundamental nature of reality itself. So, as we look to the future, it's clear that the mysteries of the Photon Epoch are far from solved. In fact, they may be only the beginning of a much larger and deeper journey into the heart of the universe's most profound secrets. With each new discovery, we move closer to understanding the true nature of the cosmos and our place within it. And as we continue to explore the early universe, we may one day uncover the ultimate answers to the greatest questions of all. How did the universe begin? What is the nature of dark energy and dark matter? And what lies beyond the limits of our current understanding? The Photon Epoch was a crucial moment in the history of the universe, a time when the cosmos began to take shape, and the first light began to shine through the darkness. It is a moment we will continue to study and explore, as we seek to unlock the mysteries of the universe and uncover the secrets of our cosmic origins. As we press forward in our exploration of the Photon Epoch, it becomes increasingly clear that the study of this time is not just about understanding how light finally broke free and began to illuminate the universe. This era is deeply interconnected with some of the most fundamental aspects of physics and cosmology, aspects that continue to challenge our understanding of the universe today. At its core, the Photon Epoch represents a time of incredible density and energy, a time when the universe was an almost incomprehensibly hot, chaotic place. This was not a universe like the one we experience now, with stars and galaxies scattered across vast stretches of dark space. It was a universe where the laws of physics were governed by forces and conditions that are still not fully understood. One of the most significant factors during the Photon Epoch was the interplay between matter and radiation. For most of this period, the universe was too hot and dense for atoms to form. Instead, the universe was a seething, opaque soup of free-floating electrons, protons, and photons. Photons, the particles of light, were constantly interacting with electrons and protons in a dense plasma. These interactions kept the photons trapped, unable to travel freely. The photons were scattered by the electrons and protons, making the universe opaque. It's crucial to understand that the Photon Epoch was not a static period. It was a time of rapid change, marked by the cooling of the universe as it expanded. This cooling allowed the particles to lose energy and become less ionized, eventually enabling atoms to form. This process, called recombination, marked the transition from the Photon Epoch to the era of neutral atoms. Recombination is often considered the point in time when the universe became transparent to light, allowing photons to travel freely for the first time in history. But before recombination, the universe was still a soup of charged particles, with photons trapped in this primordial plasma. The photons couldn't escape from the universe's dense, hot core. They were continually absorbed and re-emitted, unable to make their way across space. The entire universe, at that point, was like a foggy, boiling cauldron, with photons locked in a never-ending game of ping-pong. This era lasted for approximately 380,000 years, a brief but crucial period in the universe's history. While this may seem like a long time in human terms, in the grand scheme of cosmic evolution, it's a mere blink of an eye. In fact, the Photon Epoch was just one part of a much larger story of the universe's development, with the epoch itself playing a pivotal role in the creation of the conditions that led to the first galaxies and stars. After recombination, when photons were able to escape the plasma, the universe entered what we refer to as the cosmic dark ages. These were the first few 100 million years following the Photon Epoch, a time when the universe was relatively featureless, with no stars or galaxies to light up the space. The only things that existed were the faintly glowing gas clouds of hydrogen and helium, the building blocks of the first stars. It was also during this time that the universe began to cool to the point where dark matter could start to have an even more significant impact. Dark matter, which was already present in the universe during the Photon Epoch, began to influence the formation of the first structures in the universe, including the first stars and galaxies. Dark matter's gravitational influence helped pull together the first clumps of gas, which eventually collapsed to form the first stars in a process known as cosmic reionization. The transition from a universe dominated by a dense, hot plasma to one where light could finally travel freely was not just a technical change. It was a profound moment in the cosmic timeline, a transition from a state of near-total opacity to one of transparency. This change enabled the universe to evolve into the structure that we observe today. The study of the Photon Epoch provides us with a glimpse into a time that is far beyond our direct experience, but still profoundly influences everything we see in the universe today. Through the cosmic microwave background (CMB) radiation, we can observe the imprint of the Photon Epoch. The tiny temperature fluctuations in the CMB carry a vast amount of information about the density of matter in the early universe, allowing scientists to learn more about the conditions that existed shortly after the Big Bang. This radiation is like a cosmic fossil, a snapshot of the universe when it was just a fraction of a second old, offering us clues about the physical processes that occurred in the moments after the birth of the cosmos. Interestingly, as we continue to study the CMB, we find that there is still much we don't know about the Photon Epoch. For example, the exact mechanisms behind the formation of the CMB's temperature fluctuations are still not fully understood. The fluctuations in the CMB are the result of subtle quantum fluctuations in the early universe, but the full implications of these fluctuations are still being explored. Could they offer clues about the quantum nature of the universe? Could they help us understand the nature of dark energy, or the elusive properties of dark matter? One of the biggest unanswered questions is whether we can gain a deeper understanding of the Photon Epoch through future technological advancements. Instruments like the James Webb Space Telescope and future missions aimed at studying the CMB in even greater detail could open up new possibilities. The ability to detect subtle variations in the CMB on even smaller scales could allow us to uncover hidden details about the universe's early years, perhaps shedding light on some of the most profound mysteries of all. Moreover, the study of the Photon Epoch ties into some of the most fundamental questions of cosmology and physics. For example, the exact nature of the Big Bang and what happened in the moments immediately after it remains unclear. Did the universe experience a rapid period of inflation, expanding faster than the speed of light? If so, how did inflation occur, and what triggered it? These are questions that are intricately linked to the Photon Epoch, and as we gather more data, we may get closer to answering them. At the same time, the Photon Epoch raises intriguing possibilities for the future of the universe. As we study the early universe, we are not just looking backward in time, but also forward. The study of cosmic evolution could provide insights into how the universe will continue to evolve in the distant future. Will the universe continue to expand forever? Will dark energy eventually cause the universe to tear itself apart in a so-called Big Rip? Or will the universe eventually collapse back in on itself in a big crunch? As we continue to unravel the mysteries of the Photon Epoch, we come to realize that we are not just uncovering the secrets of the past, we are also gaining insights into the future. The discoveries we make today will shape our understanding of the universe for generations to come. The Photon Epoch is a critical chapter in the story of the universe. While it may seem like a distant, almost forgotten era, it holds the key to understanding some of the deepest mysteries of the cosmos. From the formation of light itself to the birth of the first atoms, the Photon Epoch was a time of profound transformation. As we continue to study this period in the universe's history, we will undoubtedly uncover even more secrets, expanding our understanding of the cosmos and our place within it. The Photon Epoch may have been the beginning of transparency in the universe, but it is by no means the end of the story. It is only the beginning of a much larger, more complex tale, a tale that continues to unfold with every new discovery we make. The mysteries of the Photon Epoch are far from solved, and with each new finding, we get one step closer to answering some of the universe's most profound questions. As we continue to explore the Photon Epoch, it becomes evident that the search for answers is not just about unlocking the secrets of the universe's beginnings. It's about piecing together a story that spans across billions of years, connecting the past, present, and future of the cosmos. And at the heart of this story is the photon, the particle that gave birth to light, and with it, the first clear window into understanding the universe we observe today. Understanding the Photon Epoch means delving deeper into some of the most cutting-edge theories of physics. It takes us into realms of quantum mechanics and general relativity, realms where the usual rules break down, and where the very nature of space and time itself is called into question. What happens when we attempt to unify these forces? How can we reconcile the behavior of subatomic particles with the large-scale structure of the cosmos? These questions are not just philosophical musings. They have direct implications for how we understand the Photon Epoch and the larger cosmic landscape. The universe, in its early days, was not just dense in matter, it was densely packed with energy. The Photon Epoch wasn't just about light being trapped, it was a period when the universe was dominated by radiation. The energy densities were so high that they shaped everything that came afterward. The dynamics of matter and radiation were closely intertwined. During this time, the universe's temperature was so high that ordinary matter as we know it could not exist. Protons and neutrons could not form stable nuclei, and electrons couldn't remain bound to atoms, creating a universe filled with a hot, dense plasma. The photons during this time had a unique characteristic. They were coupled with the free electrons that filled the universe. This meant that they couldn't travel freely, as they would constantly scatter off these electrons. The process that kept photons from traveling freely is called Thomson scattering, and it was one of the defining features of the Photon Epoch. The energy of the photons was so high that their wavelength was incredibly short, meaning they couldn't escape the plasma. As the universe expanded and cooled, the temperature decreased, and this led to a gradual reduction in the frequency of the photons. However, as the universe continued to expand and cool, something remarkable happened. The temperature eventually dropped enough for the protons and electrons to combine into neutral hydrogen atoms, a process known as recombination. This marked the end of the Photon Epoch and the beginning of the era where light could finally travel freely. The decoupling of matter and radiation during recombination allowed the photons to escape the dense plasma, and the universe transitioned from an opaque state to one that was transparent to light. This was a monumental shift that set the stage for the formation of the first stars, galaxies, and the cosmic structures we see today. But the journey from opacity to transparency wasn't instantaneous. The universe didn't just snap from one state to the other, it was a gradual transition. After recombination, the photons that had been trapped in the dense plasma for so long were released. This release of photons is what we now observe as the cosmic microwave background, CMB, radiation. The CMB is the oldest light in the universe and serves as a snapshot of the universe when it was just 380,000 years old. It's a relic from the Photon Epoch, carrying with it information about the conditions that existed at the time. Scientists have spent decades studying the CMB, and in doing so, they've been able to glean important information about the early universe. The CMB is a goldmine of data, revealing subtle variations in temperature that reflect the density fluctuations in the early universe. These fluctuations are crucial because they give us insight into how matter clumped together in the early universe, ultimately forming the galaxies, clusters, and superclusters that fill the cosmos today. What's particularly interesting about the CMB is that it carries information not just about the material composition of the universe, but also about the structure and geometry of space-time itself. By studying the CMB's patterns, cosmologists have been able to infer the curvature of space, the distribution of dark matter, and the rate at which the universe has expanded since the Big Bang. All of this has led to the development of the standard model of cosmology, known as the lambda-CDM model, which describes the universe as a vast, expanding space filled with dark energy, dark matter, and ordinary matter. Yet, despite the wealth of information provided by the CMB, many mysteries remain. One of the most intriguing aspects of the Photon Epoch is the role of dark matter. Dark matter, an invisible and mysterious substance, was already present in the universe during the Photon Epoch, but its exact properties remain elusive. While we know it exists because of its gravitational effects on visible matter, we have yet to directly detect it. Dark matter likely played a crucial role in the formation of the first galaxies and stars, and its presence during the Photon Epoch could have influenced how the universe evolved after recombination. Additionally, the Photon Epoch has deep connections to the concept of cosmic inflation. The theory of inflation suggests that, in the moments immediately following the Big Bang, the universe expanded at an incredibly rapid rate, far exceeding the speed of light. This rapid expansion could have caused the universe to smooth out and become nearly homogeneous on large scales. However, some regions of the universe might have experienced slight fluctuations in density, and these fluctuations could have been imprinted on the photons during the Photon Epoch. As the universe continued to evolve, these imprints would have given rise to the structures we see today. Inflation is still a subject of intense study and debate among cosmologists. While it provides a compelling explanation for the smoothness and uniformity of the universe, the details of how inflation occurred remain unclear. Could quantum fluctuations during inflation have played a role in shaping the distribution of matter in the universe? How did inflation come to an end, and what caused it to slow down? These questions are still open for exploration, and the answers to them could offer profound insights into the nature of the Photon Epoch and the very fabric of the universe itself. As we look to the future, the study of the Photon Epoch continues to hold great promise. New observational tools, such as the James Webb Space Telescope, are set to provide unprecedented views of the early universe, potentially allowing us to peer even further back in time. With these new tools, scientists hope to uncover more details about the Photon Epoch, perhaps shedding light on the mysteries of dark matter, dark energy, and the earliest moments of cosmic evolution. The Photon Epoch represents a crucial turning point in the universe's history. It marks the transition from a universe dominated by radiation to one where light could finally travel freely. This period, though seemingly distant, has profound implications for our understanding of the cosmos. From the formation of light itself to the earliest moments of cosmic structure, the Photon Epoch is a key chapter in the unfolding story of the universe. As we continue to probe the depths of space and time, the Photon Epoch remains one of the most fascinating and enigmatic periods of cosmic history. Each new discovery brings us closer to understanding the origins of the universe, the forces that shaped it, and the hidden mysteries that still lie beyond our reach. It is a reminder that, even in the earliest moments of existence, there is a profound beauty and complexity to the cosmos, one that continues to captivate our imagination and drive our quest for knowledge. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.